All right, everyone. Welcome to another week. We are going to talk about numerical data, but first, I thought I'd make an announcement that for those in New York, it's actually going to be the 10th annual conference for the New York City meetup group, our meetup group. So it's May 16 and 17. Um, so I think you count as if you do it in-person academic, yeah, it's $495, but I put a code in the chat that would get you 20% off of that. So I've gone most years. I might have missed one or two. I think it's a really good conference. It's single track, but like they've got some of the top people in the R and even Python community. Like Wes is a sort of one of the top Python programmers or developers for a lot of the science Python tools. Hadley Wickham's going to be there. Max Kuhn's going to be there. He does all the tidy model stuff. So, anyways, great opportunity. Just thought I'd alert it. And if you go, let me know because I'll be there. You can say hi to me in person. You can have lunch together or something. So, yeah, cool. So we got a meaty topic, so I want to get right into it. First, midterms. I saw a discount is Lander 20. Actually, if you could, don't register tonight. I think I might even had a 30% coupon because I gave a talk previously. They emailed me and they gave me an even better discount, but then they sent me a code that I could share with other people to get. I think it was 30%, but it might be 20%. And you guys are all students, so you count as you can get the academic pricing. And it's 2 full days. And I can't remember where it is, somewhere in Midtown Manhattan. All right, midterms. In general, I think you guys did well. I'd like to remind you, it's only 10% of your grade. So don't sweat it. We generally don't share the answers because we reuse questions. We don't really want them out there. Writing good multiple choice questions is really hard. So we don't want to write a whole new assessment every semester. So we kind of reuse bits and pieces of it. But if you have specific questions and you want to reach out, we could set up a Zoom meeting and we're happy to do that. On the left is the distribution of scores. So the mean was somewhere around 80. So that's, I think, pretty good. On the right is a breakdown of sort of the right is the percent of people who got it correct and don't get it correct. This pattern is kind of similar from semester to semester. I was looking at them today to make sure, did we have an error and maybe the wrong answer was set correct? And the answer is no. The two ones that kind of stick out, 6 and 16. So question 6, my heart broke a little bit of how many people chose pie chart as the appropriate visualization. So I'm gonna guess nobody in this meetup right now picked pie chart. So I'm not gonna say any more about it. I don't know exactly. I just looked at the distribution. Pie chart is clearly wrong. And it should have been an easy question. If you picked any other distractor, maybe I could have forgiven you, but pie chart, ouch. Um, the other one on 16 had to do with was the question of your friend flipped a coin, you know, got 20 heads and has like 80 more. Or what was it? I gotta look it up.
It was
16.
it was 14, I think, and
Yeah. Okay. Your
it
friend
was 16 heads. Yeah.
bear coin 200 times, and you watch the first 40 tosses. You notice he only got 16 heads. So there are there are 160 tosses left. Out of 160 coin tosses, how many heads do you should you expect to get with 160?
50%. So out of
Eight, nine,
160, it's 80, and you
nine,
put it to
80, right?
yeah,
And then you saw 80 plus 16 is
yeah, 96.
96, right? I think you fell for the independence assumption. Knowing what the prior tosses were doesn't inform what the next ones are. right? You still expect 50-50 for each coin toss. So I get it, right? So I think it's worth kind of revisiting it. Right? And that's a common pitfall. Look, I fall for it for sometimes, like, oh, and you gotta go like, nope, each event is independent. Doesn't matter what I got before. I'm still gonna on each of the next ones, I expect of the 160 left to be 50-50, so 80. So those are only the really two big ones. The rest of them, I think the proportions are kind of decent in terms of correct and incorrect. So if you have specific questions, reach out to us and we can set up a Zoom call and we'll do that. So now is the time to start talking about, we got to this place where we can start talking about the data project and a project proposal. I don't actually know what we put on Blackboard. Did we put a due date on Blackboard, Angela? Let's see here. I just picked an upcoming Sunday. So we said, oh, April 7th. Okay, so I'll fix this. So let's make this April 7th-ish instead of 1st-ish. So that's about 2.5, almost 3 weeks away. So for the first part, what you're going to do is you're going to you can go to the project page on the website. And there's a template for the project proposal. The proposal is really designed for you to, identify the data set you want to use, your research question, and take a stab at what kind of statistical procedure you're going to use. Now, so far, we've done a lot of null hypothesis testing, and we're going to do the last bit of null hypothesis testing tonight in terms of like quantitative dependent variables. So you could do something like that. Is there a difference between this group and this group or whatever, right? That's certainly one type of analysis. The other type of analysis you could do is regression, some kind of regression, which we're going to start next week. So you can think of regression as like, here's a variable, and here's a whole bunch of other variables that I want to use to try to predict what that variable is, right? So we don't expect you to do that analysis yet. So for now, what you're going to do is, identify that data set and then, load that data set and, try to figure out, you can see what the questions are and they're in the template, and then do some basic descriptive statistics. So you can kind of get a sense of what your data is. So stuff that we talked about in the first few weeks. So you could just look at the project proposal, download the template from here. And if you're like, oh, where am I going to get data? We have a list of a whole bunch of resources that you can look at. We don't have on here Kaggle. You can always go to kaggle.com and kind of poke around. There's a ton of data sets there. 538 is a great one. If you don't see something here you like, or you have a particular area of interest, you can reach out to us. We might have some ideas of things you can use. Recommend using a public data source, right? Occasionally, if you work somewhere and you have a data set from work that you can use, that's fine. But at this stage, you're early. I know you're early in the program, but if you use a public data source, you can publish your analysis and your data and think about, this is something that would potentially could be on a portfolio, right? When you get to the final project. So using public data sources means you can share that stuff and potential employers can see the whole thing, right? Versus if you use a data set you can't share. So that's why we encourage to do that. So that's kind of, so start thinking about that, pick a data source that you like, have fun with it. The spectrum is all over the place. We've had some of the more kind of bizarre ones. We had somebody do an analysis on, trying to predict who's going to win the Bachelorette. I was like, okay, that's different, all the way to like COVID deaths, and everything in between. So the proposal is due on the 7th. So if you look at, there's an example data proposal. So you can kind of see, you're just filling in. You're not writing a ton of stuff, but, what is my research question? What are your cases, type of study, response, and your summary statistics. So basic summary statistics. Everyone should get full credit on their project proposal. You may not get full credit on your first attempt. This is one of those situations where we're going to expect you to resubmit if you don't get full credit, because we're going to give you feedback and say, oh, you should maybe tweak this, or you're missing this, or what. And then because we want to ensure that you're on a solid foundation before you try to put together your project presentation. And so to give you a sense of where, what the end game is, you're going to give a 10-minute presentation that walks through the analysis. And you can kind of think of it as like a talk you would give to your boss, right? That might be like your target audience. So you're going to have to describe what the question is, what's your data, where did it come from? Here's how I did my analysis. Here's the results. Here are the implications and limitations. And we'll talk into that in detail. We have examples that you can use later. The way we'll set that up is in a few weeks, we'll set up a Google spreadsheet, and we usually set up about 6 or so 90-minute time slots, usually a couple trying to do around lunchtime, some in the evening. You're going to sign up for one 90-minute session. So we usually have up to 8 or 9 students per session. So what will happen is you'll get on that Zoom with 8 or so of your peers. They're going to give their talk. You're going to give your talk. And so you could hear some other students' presentations, and then you'll give yours. And we have a form for peer feedback and a whole system. So that's kind of the end game. We will get into much more detail in a few weeks, probably right after the 7th, whatever the Wednesday after the 7th is. We can show, kind of what that end product was. Yeah. So let's I'm going to hold on the lab question to the end, if you don't mind, so I could pull it up. Questions about this right now? You got a couple of weeks, couple of Wednesdays. You can always ask on Slack. All right. Not you still have time tonight, but I want to start getting into it. So for tonight, or at least for the first part, we're going to look at data from a high school and beyond survey. So this is actually a data set that comes from the Department of Ed. If you're not familiar, there's something called the National Assessment of Educational Progress, NAEP, as it's often referred to, or more in the pop, in the sort of mainstream news, they often call it the nation's report card. It's an assessment the Department of Ed does every 2 years, mostly with grades 4 and 8. And the whole goal is to try to figure out where students are nationally, or where education is nationally. It's not about assessing individual students, but it's an idea of trying to provide a barometer or a temperature of how the United States is doing in terms of education. Now, the high school and beyond actually is derived from NAEP. So what they do is they randomly select students who were randomly selected as 8th graders and follow them through high school and beyond. Okay. And they assess things in like reading, writing, mathematics, and then look at, their educational trajectory, whether or not they go to college, et cetera, et cetera. So this is just a little small data set. It's got about 200 students, and we have their reading and writing scores. And what we want to know is there a difference between the reading and writing scores between these two students? And here on the left side, I have a good, common box and whisker plot figure that we often use when we're trying to look at the two different plots, or the outcome of two different variables. And of course, remember, this is the median. What we're going to be interested in is comparing the means. Since it's a smaller data set, I actually superimposed all the figures. On the right-hand side, I actually just added this plot recently because I just discovered this package called ggdist, which has a ton of just really cool geometries that you just add on to ggplot, right? So they work in the ggplot way. And so this gives me this geom-stat half-I gives me the density distributions of the two groups, but it also gives me the mean. And then the darker black line is I think the one standard error, and then the slighter one is 2 standard errors. So that would essentially give me a 95% confidence interval. And then I added the geom points. You could see I changed it to lines so I can actually see all the raw data there. I'll come back. There we go. Okay, cool. Right. So on the surface, I look at these distributions overlap quite a lot. So I'm going to say, my null is going to be that there's no difference, but of course I want to test that. And here's what the data looks like. Here's the first 6 rows. So the first question I often ask when I'm looking to know if there's a difference between some grouping variable of some kind, or in this case, two variables, is are they independent of one another? And in this situation, they are not, right? Because the reading score, this reading score is dependent on this writing score because it's the same student, right? So there's sort of this dependence, and the dependence is the student. So if that's the case, this actually becomes a much simpler problem because what I can do is simply take the difference of the two scores. All right. And so this question is going to come up and you're going to have to deal with this. Like, how do I know if they're, independent, right? And one of the easiest clues you can have is often how the data is presented, right? So if the data is in a tidy format, which I think we talked about briefly at the very beginning, I hope you're talking about tidy data more in 607, right? So tidy data being each row represents something you're measuring. In this case, each row is a student and each column is a variable of what the measurement is, right? So if you're trying to compare the difference between two variables such that I could just look at the difference across rows, then I'm going to say those are dependent. If it's not, right, if it's something else, like if I were to pick gender, right, so if I want to know the difference in gender, that falls in one column, that's probably independent, right? Because if I can't do that subtraction row wise, well, then I'm probably looking at independent test. But in this case, we can do a dependent test. All right, so it becomes easy because I can just do the subtraction. So now I have a single variable, right? I can look at the distribution of the differences, right? And then I could set this up as a null hypothesis. And what's my null? That the difference is 0. So then my alternative hypothesis is that the difference is not 0. Great. Nothing new here, right? We've been talking about the central limit theorem, and we've been looking at how the central, right? And so I think it's worth a refresher, right? The central limit theorem states that as our sample sizes gets larger, as n is larger, the sampling distribution, or the sample of means, say, if we take a random sample, take the mean, take another random sample, take the mean, and so now we have all of these means from all of these different random samples. That distribution of means is going to approximate the normal distribution, which is great because we generally only have one sample. But from that one sample, we kind of know in the background, like the sampling distribution from which it came. And because it's normal and we know the properties of the normal distribution, right? We know the 65, 95, no, 68, 95, 99% rule, right? If we go out 1, 2, 3 standard deviations, we get so much area. That's great. The area under the curve is 1. We can interpret all that as a probability. So in this case, just to wrap this up, right, because we want to get on to other kinds. So the difference here is negative 0.54. We plug that in, we get this test statistic. So where X is, right. So we're going to look at the area less than negative 0.54 and above 0.54. And that works out to be about 0.586. It's much larger than 0.05, right? If we want a 95% confidence level, when we're looking for the p-value to be less than 0.05, this is not less than 0.05, so we would fail to reject the null hypothesis. Okay, great. There's the calculations for us. And there's our interpretation that we've had before. And then we could do it as a 95% confidence interval. So this shouldn't be new, right? We actually kind of did this 2 weeks ago. But this is a little bit new. So this is a way of visualizing it that I kind of like. So here on the surface, it's a scatter plot. So I've plotted the reading scores against the writing scores. And since there's a dependence here, right, each point represents a student, and I have their 2 scores. Okay, so far so good. Now, because these are on the same scale, I fixed the coordinates so that they're equal. So it's a square plot. So you can't see it, but the Granova gg.ds inside is using, there's an option to ggplot called coord_equal. What that does is fixes the coordinates in the X and Y direction to be the same. So as an artifact of that, we end up with a square versus a rectangle. Reason why I want to do that is I want to add the line y equals x, or the unit line. So that's this dark black line. right? And if we think about what y equals x, so what we're saying, it would be the line right equals read. So if y equals x, then the difference is 0, right? So any points that fall on the unit line mean the difference is 0. Right? And remember, what are we doing? What's our null here? We're trying to test whether or not the difference is something other than 0. Okay, great. So we have that unit line. So what we can do is draw a line perpendicular to the unit line. And for each of these observations, we're just going to project down to a point on that line. Now, its position, this way doesn't really matter. We just have it down far enough so it's out of the way of where the actual scatter plots are. So if you turn your head 45 degrees to the right, this represents the distribution of differences. That's essentially this plot, right? If we were to, draw this, right, we have 0 and we have center. That's what all of these points represent. Okay. So with that, right, we can calculate the mean of the difference, which is the dashed line, right? And the difference here was pretty small. It was like half a point, right? So it overlaps quite a bit. So this dashed line is half a unit separated from the line y equals x. And then from there, we have this little green bar, which I know it might be hard to see in this particular example. That's the 95% confidence interval. So from this visualization, because these are the distributions of differences, and the line y equals x represents a difference of 0, this green line, if it spans the unit line, means we would fail to reject the null hypothesis, right? So we can kind of, hopefully, what I'm trying to convey here is like, all of these things kind of have a visual component to it, right? And we can represent these geometrically here in all the bits. The other last two parts we have is this is a rug plot on the top and the right, which just represents the distribution of reading scores, and this is the distribution of writing scores. So if you want to use this, I find this a pretty handy plot, particularly in cases where I'm doing a randomized trial. So a lot of times I have treatment and control, right? And I kind of have them paired. And so this becomes a really kind of cool way to see it. In particular, because sometimes this one here, there's no difference. They're kind of all centered. When you do certain types of treatments, you might see some points over here and some over here. And if you could start to figure out why some are in different places, you can start to see whether or not the treatment effects are homogeneous or heterogeneous, right? So, and maybe I'll be able to talk about that a little bit later towards the end of the semester if we talk about PSA, if we have time. All right, another difference, right? I actually alluded to this before. I want to know if there's a difference. In this case, I'm going to use an SAT score data set, and I want to know if there's a difference in math scores for males and females, right? So in this case, each math score is independent of each other, right? Presumably, knowing that student 1 got a 450 doesn't really tell me anything that student 2 got a 540, and et cetera, right? So I'm going to assume independence here. So first thing I do, let's look at some descriptives. So I'm going to use my good old describe by. So I could see the mean for females is 597. The mean for males is 826. Couple standard deviations. I look at the box and whisker plot. I did also superimpose the means, right? So what I want to know is the difference in these means something other than 0? So in this situation, what I can't do is I can't like subtract row-wise and just get a single vector of difference scores. So we're going to need to look at this a little bit differently. And here's the distributions of scores for the two groups. All right. So we already talked about independence between groups. We also have independence within groups, right? Knowing, again, if you have one, oftentimes you have the other. And the sample size is sufficiently large enough. I think the textbook uses 30 as sort of a threshold. We're good. We're going to relax that 30 in just a few minutes. But for now, 30 is good, and it's not terribly skewed. So we're good to go. So we talked about the standard error calculation 2 weeks ago in the normal distribution. We talked about a single metric. We talked about it last week in terms of proportions, right? And if you remember, when we had a single proportion, we had the product of are the proportion of success times the proportion of failure divided by n. And then when we added the second, when we had two proportions, right, we had to have both of them. We had the success of failure for group 1 over the n of group 1, the proportion of success times failure for group 2 over the n of group 2. For quantitative variables, we're actually following the same pattern. So that product of proportions is akin to having some sense of spread, right? How far could those proportions go? So when we move to the standard error, right, and when we talked about the standard error 2 weeks ago, again, the standard error being the standard deviation of the sampling distribution, right? What's the sampling distribution again? It is the distribution of all of the means as if we could take an infinite number of random samples. So that distribution of all those means has a spread. We call that spread the standard error, right? And so we used the sample standard deviation over n, take the square root of all that. Great. We did that a couple slides ago. When we have two means or two groups that are independent, right? So we just got to tweak it a little bit. So we have, in this case, the standard deviation, well, squared, right? So it's actually the variance for males over n. We use the standard deviation for females on this side. We add it up, take the square root. And that gives us the standard error for the difference between males and females. And so we could calculate this all out, and we end up with a standard error of 1.55. We're going to use 1.96 as our critical value, right? Because if we go 1.96, the area from negative 1.96 to positive 1.96 from the normal distribution is 0.95. So that's our 95% confidence interval. And so we just multiply that by the standard error. And in terms of using a confidence interval, we're going to say we're 95% sure the difference between males and females is between 26 and 32 points. Okay. So 0 is not in this interval. So we would actually reject the null hypothesis under this with this example. We can visualize it, right? So we can go back to what we learned 2 weeks ago, right? And say, okay, well, I can calculate the standard error for male scores, and I can calculate the standard error for female scores. And so here's this line here, right? That's the distribution of male scores from our sample. This purple line here is the distribution of female scores. Okay, if we look at the males, right, this distribution is our guess for the sampling distribution, right? It's normal. It's centered on the sample mean. And then here, I only went one standard error above and below. And the reason why I only went one standard error above and below is because I want to compare the overlap between these two distributions. And we're actually going to use this technique later in a slightly different way. But when we do this, we only go one, right? Because normally we would go 1.96 or close to 2. But if I'm going one this way and then one this way, if I actually went 2, then I would actually be, I would have a much more conservative effort, right? So I'm allowing half of that, error to be in the males and the other half in the females. So as they come in, if I go one in the male and one in the females, and if they're not overlapping, then I'm pretty sure I have non-overlapping standard error bars. I would not reject the null hypothesis, but in this case, they are not overlapping, so this would give evidence for rejecting the null hypothesis. So the reason why it's only one is I'm kind of splitting that standard error between the two groups. All right, now we get to talk about my favorite statistician. So the question is, this is great, right? So the textbook says we need to have sample sizes of 30. But, more than a century ago, somebody asked the question, actually happened to work for Guinness Brewery. It said, I need to test the quality of this batch to the next batch of Guinness beer. And as maybe I would have volunteered and said, yeah, I'll drink 30 beers and compare them. That might have shortened my lifespan quite a bit, right? So the question is, what do I do about that, right? I can't get a sample size of 30, right? And so brilliant man, William Gossett developed what is now called the student's t-test. I suspect a lot of you have probably seen this, whether or not you've actually done it. It is the most prominent statistical test that's done if you're comparing two groups. Okay. So it's called student's t-test because when Gossett initially published this, he had to use a pseudonym because he couldn't say what he was doing. The brewery company didn't want him to publish. It was a trade secret, right? They had a new way of ensuring the quality of the beer. But if you actually go, I've been to Dublin, you can go to the Guinness and they have a plaque there for him. It's really great. So if in St. Patrick's Day was this past weekend, you probably didn't even realize if you're drinking a Guinness, you have a statistician to thank for how good it was. And so what he did is he just, we've been using, oftentimes the textbook uses Z, right? And so the Z is for Z scores is a way of referencing the normal distribution. So Gossett said, well, I need to have some kind of penalty for the smaller sample sizes. So I'm going to call this T, a T statistic, right? We've had Z statistics. Now I'm going to have T. And what I'm going to do with the T statistic is I'm going to use something called the degrees of freedom. And for now, we can just think of degrees of freedom as a proxy for sample size. So for now, we're just going to define degrees of freedom as n-1. Okay. And we actually saw degrees of freedom last week when we talked about chi-squared, right? And so here's a couple of T distributions. So it looks kind of normal, right? But let's see what's going on. So So this dashed black line is actually the standard normal distribution. This red line is the T distribution with 1 degree of freedom. And let's look at what's going on here, right? So if we've learned with the standard normal, if we go 1.96, negative 1.96 to positive 1.96 is going to give us 95% of the area under that curve. So what is this red line doing, right? This T distribution with 1 degree of freedom is a little bit shorter. So, which means we're pushing some of the area further out to the tails. So if you have 2 degrees of freedom, right, our critical value is not 1.96. It's going to be something for, if we're going to the right? So to get 95, I'm going to have to be out here like at 2.5 or so. I don't know exactly what it is. We could figure it out, but right. So that means that critical value needs to be larger or smaller, depending on what tail you're on, for me to reject the null hypothesis. And so hopefully intuitively that makes sense, right? I need to be further out for me to reject because I have less data. I have less evidence. And so, but by time we get to 30 degrees of freedom, the T distribution very closely approximates the normal distribution. In fact, it's going to be the same to like 2 decimal places is often what we're going to report. So once you get to 30, you could use either. Now, for reasons I actually do not know, we always use the T statistic whenever we report anything. Like if you're going to do a null hypothesis, if you have an N of 1,000,000, you're still going to use a T statistic. And I think it's just because of tradition. It takes the choice away. Do I need to use a normal or T? We're just going to use the T, even though the T would probably be the same as the Z from the normal. I don't know, Angela, I know this comes up every day. Have you figured out since last semester? No idea why T, we just use T and not the normal. But that's the situation. And as we go forward, we do regression. We're going to see T statistics in our regression output, not Z, T, always. If you read journal articles, report T statistics, never normal. Okay, great. So how do we do this in R? So of course we have, right, we have our Q, P, R, and D functions, but now we have a T distribution. So in the same way we had them for norm, we have them. So we could use the QT. And so if I wanted a 95% confidence, what's the critical value for a 95% confidence level, right? So I'm going to do 0.025, right? And remember why? Because it's a 2-tail test. So I want 2.5% to the left, 2.5% to the right. And so R is always going to give me the area to the left. So I use the Q. I want 2.5% of the area. So the other bit we have to have is the degrees of freedom parameter. So we're going to say 10. So for 10 degrees of freedom, my critical value or my test statistic either needs to be less than negative 2.22 are greater than 2.22, right? So I'm over here or I'm over here. If I have a critical value of 2 and I have 10 degrees of freedom, well, that gives me 96% of the area under the curve. So we can get those ways. But this is probably how you're going to do your actual null hypothesis test. So there's a t-dot test function in R. Now, we haven't really talked about formula notation in any detail yet. We'll get to it in much more. We'll obviously talk about it next week when we get to regression. But for now, the left of the tilde, right? So because the equal sign has the programming meaning in R, it's an assignment operator, we can't use the equal sign when writing formulas in R. So the tilde is just, you could think of it as the equal sign. If you were to write an equation on a paper, y equals mx plus b, as we'll get to next week, so that that equal sign just becomes a tilde when we need to represent it in R. So the tilde is an equal from a formula, not an assignment operator as in a programming way. So that's our quantitative variable. Here's our grouping variable. We pass in the test. So it gives us a t-statistic, degrees of freedom, a p-value, and then our confidence interval, as well as the group means. So this is actually using a slight variations of Gossett's original student's t-test. It's called a Welch's sample two-sample test. So it does some adjustments for different group sizes and some skewness. So actually, in this case, the confidence interval actually spans 0 here. So we would not reject the null hypothesis using this version of the t-test, which is probably what you're going to use. All right. We've got 20 minutes left. I think we can do this. So then the last thing we want to talk about is analysis of variance. And so analysis of variance, so we can compare when we have a single metric, right? If we have dependence, we can find the difference, right? We have one distribution to work with. We can do 2 groups, and we can use the t-test when we have sort of 2 standard deviations to compare. What if we have more than 2 groups? That's what ANOVA does. And we got to have a slightly different strategy to get there to know whether or not there's a difference in the means across multiple groups. And the way we're going to get there is by decomposing and comparing different variance components, right? So remember the variance, right? Way back when we talk about descriptives, right, is our measure of spread. And we often report the standard deviation, which is simply the square root of the variance. We're just going to work with raw variances here. The data set we're going to use, I promise, is one I picked pre-COVID, but it seems more relevant now. Here's the reference. It's a data set from 2014. We're going to compare the bacterial count after using 4 different hand washing techniques. We're going to have water only, regular soap, antibacterial soap, and antibacterial spray. Turns out, so we replicate each of these 8 times. So we have 8 observations for each hand washing type. And it was randomized the order of these things. So we can, right, so we can make actual causal inferences from this particular data set. ANOVA doesn't necessarily mean you get causal inferences, but if you had because our design is set up in such a way, we can make a causal inference. Okay. So what are we doing for ANOVA? So for ANOVA, all right, let's start with the descriptives. I'm sorry. So here's a box and whisker plot. So this would be a great way to look at the data. So we could see, right off the surface, we say, I suspect alcohol spray is better than the other methods, right? But, is there enough evidence? I mean, admittedly, that difference could just be because of random variation. And so that's what we need to check. So we have the medians, but of course, we're going to compare the means. I actually have the raw observations there. All right. So when we do an ANOVA, our null hypothesis is that all the means are the same. So be careful, because I'm kind of looking at this plot. I might say, oh, I want to test that alcohol spray is different than the other. If I want to test that, I could do 3 paired analysis, right? And we should do something special that we'll talk about at the end. But right now, the ANOVA, all we're going to test is are the means different? Do we have evidence to say the means are not the same? All right, so this slide is just going to calculate a whole bunch of descriptive statistics that we're going to use as we break down the components of how we're going to set up this null hypothesis test. So I'm using the describe by function here, and then I rename a column. So I could see I have method. So this DESC is short for descriptions or describe or whatever you want to. And so I have my methods. I have my n for each group. I have my mean for each group. And the describe by gives me the standard deviation. But as I mentioned, I'm going to really want to work with variances. So I actually added the variance here, which is right. So I just took the standard deviation and squared it. So I have a column of variances. So the variance within each group, right? So, right. So this mean is looking at only 8 observations standard deviation. So that this variance is from these 8 in the alcohol spray. Now down here, I'm going to have a grand variance, which is I'm just taking all 32 observations and calculating the variance, which is this, right? So that's going to become important in a minute. So the other descriptors I want, I have a variable called K, which represents the number of groups I have, which in this case is 4, right? And then N is total number of observations. Grand mean is the mean of bacterial count for all of my observations. Talked about grand variance. And then here's another interesting one, what we're going to call pooled variance. And the pooled variance is the average of this column right here. It's the average of the variances for each group. So you got to be careful there, right? Grand variance is simply what's the variance for all my observations, ignoring group membership. Pooled variance is what's the average of the variances for each group. So, right, if I were to calculate this out, the denominator for this one is 4. The denominator when I calculate the variance on this one is 32. Okay, great. So I have them all saved as variables. I need to take another small digression. In order to, I'm going to try to present a way of looking at this visually. So I need to introduce something called a contrast. And a contrast have slightly different interpretations depending on the context. But in this way, it's simply a linear combination of 2 or more factor levels such that the coefficients sum to 0. Okay. So what does that mean? So here I'm going to calculate a new variable on this table called contrast. And what I'm going to do is take the mean of each group and subtract the mean of the means. Okay. So I'm taking 37.5 and subtracting the average of these means. And that gives me a contrast. So then the average of my contrast should be 0, right? So the units are the same. In other words, right? So the means, you can think of them, the metric I have here is bacterial counts, right? So I have an average of 37.5 bacterial counts. So, and I'm looking at the average, so I'm just doing a shift. So 1 unit increase in the raw metric means 1 bacterial count. And in the contrast, it also means a bacterial count. I have the same metric. So all I did is shift it, right? So that when I look at the average, it's now centered around 0. Why the hell would I do that? So I can draw this picture. I want to draw a rectangle or square. I'm sorry. So let's break this down. So what do we have here? So it looks like right on the surface, we have a box and whisker plot that I showed before. But here, right, this box and whisker plot, the intervals between each of the boxes horizontally is the same because I just have a categorical variable. But what I've done with the contrast is instead of plotting horizontally just as different groups, the separation of these boxes corresponds to the difference in the means. In other words, so if I look at, so this is alcohol spray. So if I go from -50 to a little over 0, right? So where's the, right. So the difference between what are the two, alcohol spray and antibacterial soap. So 92 minus 37, right, is this gap right here. Okay. And then these are much closer, right? 92, 106, 117. So 1 unit change in the horizontal is equal to 1 unit change vertically. So that's just a convenience. So I can kind of have some meaning to my horizontal spread. So I have a box and whisker plot as I have it before. So these larger solid dots are the means for the group. So this represents the mean for alcohol spray, which is, what was it? 37.5. So that would be 37.5, right? And et cetera, et cetera. And then I actually have all of the other observations since there's only 8. So now what I can do here, I added actually 2 things here. One, right, I added this horizontal line is the grand mean. Okay. And because the way I have the contrast set up, it's just the shifting, right? Essentially, I took that and rotated it. So then a vertical line at 0 also represents the grand mean. Okay. Now I use my good old trusty unit line. So this is the line y equals x. So it's going to intersect at 0 and the mean. And what's cool about this is because the way I set up my contrast, the unit line is going to traverse the means of each group. So that's the mean for alcohol spray, bacteria soap, et cetera, et cetera. Okay. This is just set up. Now what I want to do, let's look at, so there's 2 types of variances we're going to want to look at. So there's the within group variance. If we just look at this part, and ignore the leftmost sigma, right? Remember what sigma says. It's just we're going to sum over. So we're taking each observation minus the mean squared, right? This is the variance we learned weeks ago. What's different here, what we're doing is, well, I'm going to take, so if I'm looking at alcohol spray, so I'm going to take observation 1 from alcohol spray minus the mean for alcohol spray squared. Add all those up. But then I'm going to do it for each group, right? So that's what this outer sigma is doing. So let's visually, so what are we looking at? So here I'm taking each observation. So in essence, if I take just this part, right, and if K is equal to alcohol spray, it's going to be the variance of alcohol spray. So this vertical line here is the standard deviation for alcohol spray. So that's equal to 26.55, right? And if I square the standard deviation, I have the variance. So I have this square. So this square represents the variance for alcohol spray. This green represents the variance for antibacterial soap all the way through. And so the within, what we're going to call error variance, or sums of squared within, is just the sum of all of these squares. And then we're going to take the average of it, which gives me this solid square, and I'm just going to put it in the center. So this center square here is the average variance within each group. Okay, so I took the variance of this group, this group, this group, this group, and averaged it, and I get this box. And I'm just going to put it in the center. So what is this variance represented? Why are we calling this error variance? So the points are spread out vertically, right? I have the mean bacterial count, but I don't, I never observed exactly. I have 8 different observations that have some spread. And why are they all over the place? We don't know, right? Hence the error. It's could be measurement error. It could be a problem with our instrument. It could be the temperature at the time we took it. Who knows, right? That's why we call it error. We have no idea why these values are spread out. But, the law of large numbers, we take the mean, and so we think it's there, right? So this is variance or spread that is unexplained. We just don't know what it is. And all we did here is said, well, we have 4 groups. Each of them have variance, and we don't know what it is, and we're just going to take the average of those. So that's sort of that unknown error variance. Great. So then the next bit of variance we're interested in is the between group variance, right? So we clearly see, right, they're spread out. And here I'm representing it kind of horizontally, but if you turn, you can see it vertically, right? The alcohol spray the mean alcohol spray is spread away from the other three, right? So there's sort of this variance between the means of the groups. And how do we get that? So here, what are we doing? So it's kind of the same structure. We're taking, but now it's the mean of each group minus the grand mean squared. And then we multiply it by the number of observations in this group. So in a lot of ways, this bit, because we have equal group size, is just going to kind of go away. But if we have unequal group size, this becomes a little bit bigger of a factor, right? So it's kind of a weighting. But for now, deliberately, we picked a data set with equal group sizes. So we just sum all of those. So now we have the variance between the groups. Okay, so let's break that down. Like visually, what are we doing? So we're taking the mean of each group minus the grand mean. Well, here's the mean of alcohol spray. Here's the mean of the grand mean, right? So I subtract that and square it. So for alcohol spray, its contribution is the area of this rectangle or square. And we do it for the other three groups. And then we sum all of those. And again, I'm just going to center it in the middle. And it's this green box. So this green square represents the between group variance. Great. So we have two variance components, an error component and a between group component. So this table is a way we're going to see this structure a lot of how we're going to report ANOVA, right? So these are just repeating from before, but I also added just so we can see the total variance that we learned in week 2 or something, right? Each observation minus. If I take the sum of if I add this and this, it should equal this, right? So we're breaking down the variance components. And then we have degrees of freedom that we have here. So for the between group, our degrees of freedom is k minus 1, right? Because we have 4 groups, right? And so we're going to have 1 minus the number of groups we have, right? So we're comparing 4 variances versus the within group error, which is going to be n minus k. Because we used k of those degrees of freedom up here, we need to take them out of here. So this is going to be 32 minus 4, or we're going to have 28 degrees of freedom for the within group. Right. So hopefully you see these are sums of squares, quite literally, right? We call them sums of squares. Why? Because we're squaring a whole bunch of stuff and taking sums, right? So literally sums of squares. But those can be quite large. So we want to kind of average them out. So we're going to calculate what we call a mean square, right? When we take a mean, what do? We sum all our values and divide by how many observations we have. We're doing essentially the same thing here. We're taking the sums of squares and dividing it by the degrees of freedom, right? The degrees of freedom is simply a proxy, really, right now, you can think of for sample size. All right, great. So we're going to calculate a new test statistic, right? We can't use T, we can't use Z, we can't use chi-squared. So we have to, introduce another test statistic. We're going to call it the F statistic. It's actually named after Fisher, statistician from the last season. And the test statistic is simply the ratio of these two mean squares. Okay. It's the ratio of the area of these two squares from this plot. Okay. And that's what we're going to call the F statistic. Now, if the variance, right? So this middle kind of orangish yellow square is probably going to be the same no matter what. But if the alcohol spray was actually not so far away, then this green square would get smaller and would be closer to this, right? So visually, right, if that between variance is large relative to the error variance, right, that would suggest there's a difference between the groups. But if the between group variance is equal to the error variance within each group, meaning the separation in the groups is no different than the separation of observations within the group, then that's evidence that the null is true and that we would not reject the null hypothesis. All right, so we're comparing the spreads within the groups to between the groups. And we need the between groups variance to be larger to have evidence to say, well, the variation between the groups is greater than what the unexplained error variance we see within each group in terms of whatever measurement or what have you. That's essentially what we're doing here. and we can represent it by these squares. Okay, thanks, Anthony. I will make it darker going forward. Sorry about the contrast, should be better. You could pull up the slides later. It could, but I will take that feedback and make the green darker. All right. Because of the visualization, I actually gave it to you. So here are all the parts that we broke down here. So our null is this, and I can't emphasize this. We're just testing that the means are the same. Okay, and here are all the bits, and we're going to go through. So we need to talk. All right, so this is kind of summarizing. So because we're assuming equal variance, we have that pooled variance, which in this case was 114.10. So, and I think I already said this. So if the null hypothesis is true, right, this ratio should be close to 1. If the null hypothesis is false, this ratio is going to be larger than 1. Now, let's think about like this ratio. So this is a sum of squares, an average of sum of squares. We are, okay, good question, Ely. I'm going to punt on that for a second. For now, we're assuming for convenience. But it is also has to do with this bit right here, so if we have unequal variances and we have unequal group sizes, then if the ratio of like one group to another becomes quite large, that could bias these variance estimations to certain groups or another. So it's a combination of those two things for that assumption. So I kind of answered. Because I'm doing the breakdown, when we get into, you actually call it an R, like with the Welch's T statistic. We've made some advances that put in penalties for sort of violations of those assumptions. The ANOVA procedures in R will do the same. We'll take in some penalties. And Angela, maybe you can correct, because I think you've done much more ANOVA in practice than I have. My experience, ANOVA is pretty robust to violations of these assumptions.
Yep,
So
that's one of the first things I learned when I learned ANOVA also. So there are, as with all of the hypothesis tests, right, we have a list of assumptions that we have to sort of run through to see if they are assumed, and if not, then like Jason said, we have adjustments that we can make. And so for ANOVA, that's one of them.
all right, I'm sorry, I'm making green square big darker. Okay, great. Oh, that's what I was saying. Breaking this down. This is comprised of squares, right? What's one of the features we talk about why we square things, right? It does two key features. One, it makes all the values positive. And secondary, it means points that fall further away are kind of, it's not a linear contribution as things get further away. It's sort of a geometric, right? So as a result, right, this ratio can't be less than 0, right? It's always positive. So like the chi-squared we talked about last week, the F distribution is bounded at 0. So it's always a one-tailed test. Okay. And so this is like chi-squared and like the T statistic, we have to deal with this notion of degrees of freedom. But unlike the others, we actually have 2 degrees of freedom. We have what's called the numerator degrees of freedom, but that's the degrees of freedom between groups, and the denominator degrees of freedom, which is the degrees of freedom within groups. Right. So if we go back here, right, so the T is treatment or between groups, the E is error or within groups, right? So we're taking that ratio. So that's what we mean by numerator and denominator. So for our example, we have 3 degrees in the numerator and 28 in the denominator. So this is the F distribution for which we're going to evaluate our null hypothesis. So here, okay, I have a picture of it here. Did I calculate the test statistic yet? Not yet. Did I? I must have. Why can't I find it? Well, it's in the plot. Okay. well, we'll get there in a second. So for this particular problem, right? So remember, like we've kind of, or at least maybe I fixated on this 1.96 as our critical value when we're using the normal distribution. So for this problem, where we have 4 groups, 32 observations. So we have 3 degrees of freedom in the numerator, 28 in the denominator. We need our F statistic, or that ratio of the mean squares, to be larger than 2.9, right? So at 2.9, the area to the right of that in this F distribution is 0.05. So if we have any critical value greater than that, then the area to the right of it is less than 0.05. So that's the range we need to be in to reject the null hypothesis. Okay. So that's what this picture here shows, right? So that's that 2.94. So it should be the same as the Shiny app, I hope. Okay. So here now we're filling in the rest of the table, right? So we have sums of squares, between, within, here's our total, degrees of freedom, mean squared, F statistic, and then we report the p-value. So you're not going to do all of this kind of manually. You're just going to call the AOV function in R. Be careful, there is a function called ANOVA, but that works with outputs from other objects. We'll actually use that when we do multiple regression in a few weeks. If you're just doing an ANOVA like we're talking about tonight, you just want to do a null hypothesis group, you're using the AOV. Syntax is the same as the T, right? We have our quantitative variable modeled from our grouping variable and the data. So not syntactically, it's very, very similar. And here I'm piping it to the summary function because that's this is the output, the way I prefer the output. And you can see this just mimics the table. I have my degrees of freedom. It gives me the sums of squares, gives me the mean squared, gives me the F statistic and the p-value. And we can go back, you can compare it to all the values that I kind of calculated stepwise as we go through. All right, I know we're 5 after, we probably have about 5 more minutes, so I'm sorry about that. Okay, great. So yeah, we kind of talked about all these assumptions. So I think we're good. If you want to know, okay, actually I do want to show this real quick. So give me 10 seconds to pull up. Oh, shoot. Give me 1 more second. Yeah, this happened to me. So I need 20 more seconds. And I need to get this. Okay, I want inst shiny ANOVA app. Oh, bummer. That worked the other night. All right, never mind. Not going to show the shiny app. We're over time anyways. It worked yesterday. All right, here we go. Multiple comparisons. Great. So we saw the original plot and we were tempted to say alcohol spray is different than the others. That's what we would like to say. But that's not what ANOVA gave us. It told us there's a difference, but it doesn't really tell us anything and the nature of the difference. So if we want to do that, right, we can do now paired null hypothesis test, right? We could do a t-test of alcohol spray to antibacterial soap and alcohol spray and soap and alcohol and water. Now, what you need to realize is each time you do a null hypothesis test, right, we're typically using a 95% confidence rule, which means there's a 5% chance that we're going to commit a type 1 error rate. So if we do one null hypothesis test, that's a 5% error rate. And then if we do a second null hypothesis, that's another 5%. So if you can imagine, if we do 20 null hypothesis tests with 95%, I would expect one of those null hypotheses of committing at least one type 1 error rate. But I want to say overall, I want to keep my confidence level at 95. So Bonferroni suggested the way you can do that is you kind of split your p-value or your confidence across how many null hypothesis tests you want to do. So in this case, if we're doing a 95%, we're allowing 5% in each tail. We want to do 3 comparisons. So for each null hypothesis test, instead of testing whether or not p is less than 0.05, we're going to test whether or not it's less than 0.017, right? And that ensures that overall, across all 3 paired tests, the overall type 1 error rate is still 5%, right? And so we could see that pictorially. So this is the same box and whiskers, except now I added these error bars. And so here, I am adding one critical value. So here, I'm using, so here's a 95%, and I have 15 degrees of freedom. Right. Okay. 15 degrees of freedom. Why 15? Because I have 8 observations in each group. So if I am comparing 2 groups, I have 16 observations. 16 minus 1 is 15 degrees of freedom. Okay. So this would be no adjustment, right? And the way you see these plots is I'm looking to see, as we saw before, do these error bars overlap? But if I do that, right, I could potentially be inflating my type 1 error rate. So if I'm just going to do 3, I'm just going to say I'm going to compare alcohol spray to the other 3, right? So then I could do this. So you can see what I did up here as I changed my critical value. I took that 0.05 divided by 3. And I could see if I do that, right, it looks like to me these 2 error bars overlap. So I would say alcohol spray is not statistically different than antibacterial soap, but it is different to soap and water. Okay. That's assuming I'm only going to compare alcohol spray to the other 3. If I wanted to do all the combinations with 4 groups, there's 6 different comparisons. I use the choose function here, right? So now my critical value, these bars are a little bit wider. So here now, I'm not sure. I can't quite see. I'd have to look at the actual numeric values, but I would say alcohol spray is touching the soap. So now under this, the only ones that are different really are alcohol spray and water. Okay. In ensuring that I still have a 5% type 1 error rate. All right. That was a lot. So please ask questions if you have them. Right. So in the ANOVA, okay, I want to look. I just saw Kaylee's question again. Oh, this one works out okay because it is equal. Yeah, this AOV function will help with the unequal variances. What happens is in the procedure, and the reason why I don't do it because it gets way complicated, and I'm not entirely sure how to do it. But the problem when you violate that unequal variances is where do I have it? This right here. You have to calculate this differently. So here, right? So what am I doing? I'm averaging these variances. But if I have different group, the reason why I can do that, right, is these group sizes are the same. But if like I had 16 observations for alcohol spray and 8 for the others, right? So then this, when I pull the variances, right, for one thing, in the grand variance, alcohol spray is counting more. So that's problematic, right? So this isn't weighted. So it's a comparison of the grand mean to the pooled variance. So if I have more observations here, well, though that particular group is contributing more to the calculation of the grand variance, whereas the pooled variance is treating them all the groups the same, right? And because a key part of this is the comparison of those 2 variances, when you violate that unequal variance, really what you should be doing is a weighted contribution, right? So right? So when we just do the variance, every point contributes equally. But if I were to double alcohol spray, so there's 16 observations and 8 in the other, one way I could overcome that is that each observation in the alcohol spray, when I do this calculation, counts half as much, right? So that the groups are kind of equally represented. And so anyways, the point is it makes the calculations way harder. And the AOV function is going to take care of that for you. So, all right, 1 minute paper links in there. Making sense? We'll see ANOVA again in a few weeks when we do multiple regression. So it's not, as a data scientist, it's actually something we can use to get various fit statistics. It's going to come up in regression models and other ways. So even if you don't, you're like, I'm never going to be doing these kinds of group differences. You're going to be, you probably will in terms of predictive models. So I think it's worth kind of understanding what's going on.
Jason.
Yeah.
Can you go back to the beginning? I missed what you were saying about the differences about trying to tell what's independent and what's dependent from rows and columns.
Oh, yeah, sure. So
thanks.
So my tip is, yeah, we'll look at this one. This is fine. If the difference you're looking at can be derived by looking across the row, then they're probably dependent. If they're a difference you're trying to infer between different values in a variable, then they're probably independent. Right? If they're dependent, right, in the case of reading and writing, because these represent a single student, right? So if you know the student's smart and you know they got a high score in reading, you're probably going to infer they got a high score in writing.
Oh, okay.
Does that make sense?
Because it's the same student. Yeah.
It's the same student, right? So if you can do that, I could subtract 52, or, subtract 52 from 57. Now I just have a variable of the differences, and I can analyze that variable.
But are these criteria that you just described only applicable within the same data set? Like,
well,
could you
typically,
compare?
yeah, you would. I mean,
yeah. Okay.
Yeah. I mean, you can do things across different data sets. In the case if it's it could be independent, right? So you could do the comparison of standard errors. Just to be aware, like when you do it, I didn't show this, but on the t-test function, so you could do the formula, or you can pass in two sets of vectors, but note here they have this paired parameter. So if paired is true, it's presuming dependence. If paired is false, it's presuming independence.
Okay.
So you often see these referred to as dependent sample test or independent sample tests. So it's not, it's just, and in some cases, independence is an assumption. In this case, it tells you which path you're going to go down in terms of how you're going to analyze the data.
Okay, that's helpful. Thank you.
Yeah, you're welcome. All right. Well, are there other questions?
Do we have time to go over
oh yeah, let's
lab 6?
Question 9, lab 6. Need some data. Okay. Okay, you gotta remind me here. Which data set was the sleep one? There's no helmet.
So in the YRBSS, yeah. So I think like we had to kind of do like the yes no ourselves.
Yep. So where hours sleep is in here, school. Okay. So let's look at, so I would do table YRBSS, school night. Okay. So to get there, right, so it's asking for 10 or more. So you're going to have to first, we'll just go through it. If people haven't submitted, they're going to get a freebie. But so I would say YRBSS. Oh, I should do. I'm going to try to do it in tidyverse. This might take me a little bit longer if I did it in base R. Nope, I'm doing it in base R because it's late. And so YRBSS. So I'm going to say sleep. I'm just going to call it sleep 10 is going to be equal to if actually no, what I could do is I could say YRBSS school nights if it's equal to 10 plus, right? So let's just make sure I did that right. Just doing a quick contingency table. Okay. Oh, this is where you might have. So they updated the data set in the package. So we have some missing values. So we could probably get rid of those. But right, what statistical test do you think we need to do here?
I believe it's chi-square.
Yeah.
I
Oh wait, hold on. I'm sorry, let me reread the question. Strength, likely to strength train. Okay, so the other variable, where's strength train?
Strength
Strength
it
train,
would be
7D.
that one, 7 days.
So let me look at that. YRBSS, strength trained, if any. Okay, so I have some missing values there. So I have two categorical. So again, really what I really want here is I'm just going to call it strength trained is equal to this.
7.
Wait, does it say strength trained every day of the
Every
week?
day. Yep. So
So I
it
would
would
say
be equal
7.
7.
Okay. So now I'm just going to change this here. Okay. So with a chi-squared, right, I have two true falses here. So really what I should want to do is I want to look at the, oops, find my copy, this against this, right? And unfortunately we have some missing values, but I think we can get rid of that. So I think the chi-squared will do it for us. So, right, so if we look at the chi-square test, right, so so I would do chi-square test. So I need my X. So X would be the sleeping. My Y is going to be the training. And then I think if I pipe this to summary, nope, I don't want that. I always forget on the chi-square. Okay. Oh, okay, so this is fine. So we get a chi-square of 23.23, and here's our p-value. So that p-value would reject the null hypothesis. Note this is scientific notation. You gotta move the decimal places 6 places to the left.
I guess my question was also like earlier in the lab we did the whole infer package, so you specify
Sure.
and then you generate like the 1000
Which
samples, which I guess is your null.
Yeah.
So I was having trouble like getting the actual like from that package getting to the chi-square statistic.
Right. Okay, I forgot. That's right. It was using the infer, and I went way down base R. So I got to remember. So, Angela, do you remember how to do this with the infer package? I forgot off the top of my head.
Looking. I don't remember either. I
Uh,
think it
I
might
think I
be.
was able to like generate the null, I guess like distribution, but yeah, I couldn't like actually get like the p-value.
Okay.
So
Yeah, I think it's
there.
because there were missing values. So,
Okay.
hold on, give me, oh wait, I have a browser right here. So this is what you're catching me where I don't quite know. So what am I? I'm going to consult Google now. So I'm going to do chi-squared with infer package. No, I don't want that one. Yeah, here we go. So it takes a data frame course to a tibble and the formula. Okay, great. So if I take, let me close that tab. All right, so if I say YRBSS pipe to chi, well, let me see, infer chi-square test formula will be strength train modeled from sleep 10. Yeah, gave me the same thing. Oops. So yeah, I don't.
So I
Yeah.
guess for this we didn't have to do the whole like generate a
There's a
random
infer.
sample with 1,000 reps.
If
Like the
Oh,
whole
you could
process.
do the bootstrap.
Yeah.
It didn't ask you there, but I think other ones did ask you. I thought the bootstrap was from
Yeah.
last week. Am I misremembering?
There's stuff up there, but then also like when I was googling around, it seems like you had to use permute instead for hypothesis testing. But because I think earlier in the lab we kind of do
Yeah,
like that
we
bootstrap
could do it through the
method.
bootstrap
So
as well. I don't remember off the top of my head. I'd have to go back and redo the first part of the lab.
okay,
yeah.
I'm sorry. I can do that,
no
or I
worries.
can get the key.
Jason, would you search? I think there's a help that's helpful here. If you search here, I'll put it in the chat. Within this R Studio, there's a nice vignette. If you type this in to the help to the
Tidy
search
chi-squared infer what?
with right here,
my
tidy right there.
here?
Yes. Yeah. So this might help, I think.
Oh yeah, this is right. All right. So here's a challenge with R. We're now seeing, and now we're going into a third way of answering the same question.
Yep.
Which sometimes is super frustrating, admittedly. So we could say RBSS, I guess. Specify this formula. Hypothesize null equals independent. Did I spell that right? I can't see. And calculate. All right.
I think this is where you also have to like the yes no specify success equals yes.
Oh, right. So I can go mutate. Really? Yeah, that's
anyway, yeah, like it was yeah, kind of tricky, like with if
has to be
we try to
like
follow
this,
this.
right?
Yeah.
Yeah. And then sleep 10.
Naomi, I think proportions could work too.
Okay.
Yeah.
Thank you.
Okay, so I need to look at, I guess I'm not I'm misunderstanding what the specify function does this way. Oh, I guess, okay. Oops. Let's try this. So if I say specify response equals strength change, explanatory equals sleep 10. Still doesn't like it. A level. Oh. Okay. So now I do need to mutate. So how do I specify that? I can't remember. It's probably up above in the lab if I remember.
So like earlier in the lab, I think we don't do like proportion across two different groups. We just
okay.
do it for one.
Right. You know what? I think that's now I remember. Oh.
I added success equals true to my specify like my specify.
Oh. There we go. Thank you. Forgot about that. Who said that?
Me, Naomi.
Thank you, Naomi.
No problem.
If I don't do the mutate, then right, so you did this. Oh. Success must be a string. So the infer must convert it to a character. Okay. So there's the chi-squared, and I think you can say get CI. Actually, I don't know if you noticed this. You can print, so I can get the stat and the CI, and then I could do print. Is there a get P? Is that what it is? Yeah, there we go. Oh, it wants direction. It should be. I have to do it explicitly. What are the values? Direction is two-sided. No. Right. The chi-squared. And it doesn't like the missing values. So this is where I think I had that slide. So my recommendation on this is we can do select. We're going to select these. There's a lot of ways you could do this. You could do this up above. And I'm going to say drop NA. Oh, and it still didn't like it. This P, it doesn't like this P value, and I don't know why. But that's okay. You got the, oh, and it doesn't like my drop NA now. Ah, right, because I think with drop NA, I have to say the variables. Is that right? Still doesn't like it. All right. This works with the confidence interval, so. Although that confidence interval looks wrong to me.
Well, and then also in the earlier in the lab, like when we did confidence intervals, we did like the bootstrap method.
Yeah, there's two ways to do it. It doesn't like that. But that is because that's what I got here, right? Yeah. This is the chi-squared. Did I just make this worse? Simon?
I mean, I think like the example of just getting the chi-square like that makes sense. But yeah,
Yeah.
like I don't know. I had trouble during the lab like getting to that stage. So I don't know if others did as well. But
No, I had
it
the
was a
same
bit trickier
problem.
on this one.
Yeah. So the one error that I get receiving was like was saying something a dichotomous categorical exponential variable, something like that is not right. I couldn't figure it out.
Can you email that to me?
I can actually put it right. I can put my code and also like the error right in the chat. So
Yeah, I can try it.
of course, I can also send it to you. So this is the error I get, and I can paste in the chat, but technically those are the same variable that you use. You just need to replace my strength 7-day with the same
Yep.
variable that you have, and night 8 hour more with the same that you have. So technically, it gives you just yeah.
Oh,
What's looking for? Oh. So yeah, maybe change it to true. Yes. Hey, did it work?
no.
No.
Yeah, I got your error.
Oh, so yeah, the category response. You see that they the same error. Proportion, well
Yeah.
defined
Oh, wait.
categorical response. That's the error that I received. That's the error that I got many times. I couldn't figure it out.
Yeah, because you need to do a chi-squared here, not a proportion.
Oh,
Naomi
Change-
did a
change the
proportion
calculate
though, and
to-
it worked, right?
What's up?
Naomi did a proportion and it worked.
Yes, I did a diff in proportion. So
And
the
it worked?
stat equals diff in props. Yeah, I can just paste my code into the chat too. But yeah, my
So I got-
binary variables were called sleep 10 hours and training every day.
And then this should be, for me, should be, I think, this.
And before that, I think I removed NAs from those two binary variables.
Yeah, but it's not.
Yeah.
Yeah. So what did you replace?
So I did drop NA from the strength chain and sleep 10 binary variables before I did this.
It's drop NA, isn't it? Like,
Drop underscore NA. Yeah, I saved it as that. And so it didn't contain 0, and so I rejected the
yeah. Okay. And so we need to talk about this. We need to fix this bit of the lab.
Yeah, if I
I'm
could
pretty
just
sure you're supposed to do a chi-squared here. So even though this ran, I think
This is actually in the vignette for infer, and so unless it's misled, it's misleading. That's not what it's supposed to be. And the vignette for infer does guide us to use this method that Naomi showed us.
the bootstrap. Yeah.
Yeah.
Yeah, Amy and
Actually, I
Jason,
guess this difference in proportions. I guess I gotta see what I guess that could be, it could be the chi-squared underneath. But there is chi-squared. All right, I will get back to you. I'll look into this.
Yeah, it was a tricky one, this one, so.
I
So
felt
I'll
that
go
it
back
was
and look at.
more than
I think I
just
have a key. I have a
tricky.
key because I did these like a year or more ago. So it may also just be late, and I just need to look at it again.
Yeah.
But I would have used the chi-squared just looking at this in isolation. Oh no, I lost it. All right. Other questions? I'll get back to you, Simon. I think, or I'm pronouncing your name wrong? Is it Simeon?
Semyon.
Simeon. Sorry, my apologies.
No worries.
All right. Well, if people partake, sitting over here, celebration of William Gossett, have a Guinness beer tonight. Angela doesn't like it, so I used to bring her one. Oh, you got it!
I have
Hey!
one. This is the one without caffeine, because if I drink the one with
Oh yeah.
yeah, that would keep me up.
All right, folks. Have a good night. We'll see you
Good
next
night,
week.
everyone.
Thank you.
Good night. Thank you.
Good night. Thank you.